Why, hello friends, Jen Foxbot here. Welcome to another edition of Math Mondays. Da 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 da. Yeah! All right, thanks for joining me today. We are going to talk about simple harmonic motion. Yes, super cool. So the reason why I want to talk about this topic is because I got a request for Fourier series and Fourier transforms. Totally fine if you've never heard of those. They are a fairly complex mathematical concept, but they pop up everywhere in physics and in engineering. When I was studying physics, I learned that Fourier series are how we convert sound waves into digital electronic signals. It's so cool, and I was blown away. So a Fourier series is basically a mathematical summation of different terms to break down a complex signal, a complex periodic signal, something that repeats over time, into a reasonable and tangible mathematical equation. So sine and cosine look like this. Cosine is just offset. So these are periodic functions. They repeat over time for infinity, more or less. It depends on the system we're looking at. But there are lots of other types of periodic functions. You could have a sawtooth wave like that, or you could have something like this. We can use a Fourier series to represent these periodic functions. And then in that way, we can actually encode them into electronics so that we can have these periodic functions represented by electronic signals, which really are only in binary numbers, so ones or zeros. Anyway, so to really understand what Fourier series are and how we use them, it's helpful to really understand what simple harmonic motion is. And so really quickly, it basically just means that an object that moves in a manner that repeats over time. So if you know how that first repetition looks like, you can apply that to all time t. Cool. Okay, so now that hopefully we're on the same page, let's actually draw a picture and break this down. So I'm going to draw my picture over here, and hopefully I'm seeing this at a different angle. Oh, that's a terrible graph. Okay, hold on, let me try this again. It's a little hard when I have to reach, but we'll do it. Okay. Okay, that's a little better. Okay, so my vertical axis I'm going to call my y-axis, and my horizontal axis I'm going to call my x-axis. And then I have a circle, which does not look like a circle, but that's okay, it's close enough. Assume that the center is at the origin. Assume, that's fine. And let's say that we have an object, I'm going to call it an object O, that moves around the circle at a constant velocity. And that the radius of the circle is going to be a. We're going to do some physics here, so we're going to work with a lot more letters than we are numbers, but that's okay, because you can always plug the numbers in later. And then the angle at which our object is at is going to be theta, which is an O with a little semicircle. Hopefully y'all can see that. It might be a little small. But then we also, I'm going to extend this out further. We also have another object. Oh, that's a terribly crooked line. All right, I can draw better pictures than this. Boop. Okay, a little better. Okay. So let's say that the top of our line, we're going to call it R just for funsies, and we'll call that S. And let's say that our object, oh my gosh, that is not a straight line. That our second object is Q. Yay. Okay, so as O moves around the circle, Q, the height of Q, it's stuck along this line, so it's not moving in the horizontal direction, but Q is moving up and down so that the height of Q is the same as the height of O. And when I say height, what I really mean is the y coordinate. So the y-axis is our vertical axis, and so therefore the y-coordinate of O and of Q is going to tell us the height at which these objects are on the vertical axis. So you can envision, I'm not going to draw different pictures, but you can envision that as O moves around the circle, it hits this top point, Q is up here, and then it starts to travel more in the negative x direction, but again, Q is stuck only moving up and down. And so as O moves around, the height of it decreases, and so Q will follow accordingly. Once O gets over here, then Q will also be at the 0 point on the x-axis, the 0 point on the vertical axis, the y-axis, and then O moves down here, Q reaches its lowest height, and then O comes back around to the origin, and then Q goes back to the 0 height point, basically. So Q moves up and down, O moves around in a circle. And we want to figure out how can we match, or how can we create an equation that allows us to predict where Q will be at any time t. Let's say we just let this system run and we don't want to pay attention to it, but when we are in class, we want to know where Q is so that we could perhaps act accordingly. I don't know what that means exactly, but this kind of resembles a system in which you have like a motor spinning and it's moving something up and down. So if you have a power plant that relies on a robot whose arm moves up and down like this, you do want to know where that robot's arm is going to be at all given points, because let's say you have to grab something from under the robot. You do not want to grab that object when it's at its lowest point. You want to hit it when it's at the top. And you also want to know how fast it's moving so you know how quick you need to be. If you should use a stick or if you should use your hand because it's moving really slow. So this is actually a really useful problem to solve. So the first thing to note is that we are given a little bit more information. We are told that our object O is moving with angular velocity omega. And so unlike regular velocity where you have units of distance over time, angular velocity has units of degrees or radians over time. Okay, so we are also told that when t equals 0, theta equals 0. And so that also tells us that for any given time t, then we know that theta equals omega t. So basically the angle at which the particle is moving or located can be calculated by multiplying the angular velocity by the time. And if you're wondering about why this is, it helps first of all to think of units. So we want units of degrees or radians here. Our angular velocity is in units of radians per time, radians over time. So we have to multiply it by the particular time to get the right units. And then you can also kind of think about how you would get distance if you were given the velocity. So a really quick aside, if I told you that the velocity was v, you know v equals x over t. So if you wanted to solve for x, you just multiply by t. Literally the same exact thing here, except we're moving in a circle, so replace x with theta, where theta is an angle. So that's why that is the case. So then we say, okay, well, let's ignore Q for a second because Q and O are related, and O is a little bit more intuitively easier to grasp. So what we're going to do is we are going to find coordinates that represent the x and y position at any given time. So to do that, we break out our handy dandy right triangle. Our right triangles show up all the time. And I always go back to my first year of algebra when I learned SOHCAHTOA. So SOHCAHTOA is this. And you're like, what? Whose name is that? No one's name. It stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent is equal to opposite over SOHCAHTOA. opposite over adjacent. So that tells me that if this is x of our particle, this is the x distance of our particle, aka the x coordinate, and this side is the y coordinate of our particle, then I know that x is the adjacent side to our angle. So x of our object, the horizontal, oops, I almost dropped my chalk, the horizontal position of our particle can be represented using sine and cosine. So we just have to figure out which one. So sine is opposite over hypotenuse, so that would be that side. Cosine is adjacent over hypotenuse. So actually, before I write this, I'm going to really quickly write out what that means. So sine of theta equals y of our particle divided by the hypotenuse, and cosine of our angle equals x of our particle, the x coordinate of our particle, divided by the hypotenuse. So to solve for the x and y coordinates of our particle, all we have to do is solve for x and y here. So the y coordinate of our particle for any time t becomes a times sine of theta, which, remember, we know that theta is equal to the angular velocity times time. So we're going to replace theta with omega t because it's equivalent. And similarly, our x coordinate, I could just erase that. Actually, no, let's keep that straight because we have two objects. So this is the y coordinate of the O object, x coordinate of the O object. That equals a times cosine omega t. That's it. So for any given point in time, we don't need to know anything else except for the time that we're taking a measurement, and the angular velocity, we would be given that, and then the radius of our circle. And given those three things, we can calculate where O is going to be. Pretty rad, right? Ha, there's a silly little pun in there. And likewise, if we had said that, well, the x coordinate of Q is fixed, so we don't really need to worry about that, but the y coordinate of Q equals the y coordinate of our object, well, then we would just say, we already figured that out. Easy peasy. So y of Q equals a times sine omega t. Pretty awesome, right? So what is fascinating to me about this is that I think it's fairly reasonable for us to think about the object O as moving in a circle. And okay, circles, sines and cosines, angles, that makes sense. Okay, I get that. We've done that before. But now all of a sudden we have something that's moving in a vertical line. There's no angle really associated with it, I guess. It's moving in a vertical line, but all of a sudden, because our object is moving in this periodic motion, or this simple harmonic motion, we find that we actually are going to be using sines and cosines to represent the motion of our particle. If instead of a vertical motion, I had said, oh, well, now I have a particle that is moving in a horizontal motion, maybe I'll call this particle L, when we could say that the motion of L is just equal to the x coordinate of, I guess if it was matched, it would be over here. Then we would just say that the x coordinate of L for any given time is just equal to the x coordinate of our object that's moving in a circle. So even though it looks like our object's moving up and down in a straight line and we expect to get, I don't know, maybe an equation of a line or something like that, because the motion repeats over time, we actually end up using sines and cosines. And that is the mathematical definition of simple harmonic motion. Basically, any motion of an object that can be represented with sines and cosines. And you might see something a little more complicated, like, say, for example, sine omega t minus phi. And that's totally fine. This will crop up later. It comes up all the time, especially when you have motion that decreases over time. So let's say, for example, if you have a spring that kind of goes down like that, that's often associated with that type of motion, like damping or whatever. But won't get into that quite yet. Cool. That's pretty much it. That is simple harmonic motion. And this is how we build up an understanding of how vertical, horizontal motion, if it is repeated over time, we can use the same type of equations that we use to represent repeated circular motion. I think that is so cool. There are connections in mathematics and physics all over the place, and this is one of them. All right, so I'm going to leave it there for now, but please let me know if you have any questions about any of the simple harmonic analysis that we did. If you are curious about, I guess I haven't done a video on sines and cosines, so if you're like, oh my gosh, what is that? I'd be happy to dive into sine and cosine if you need a little bit more foundation. I'm sure there are other videos online that also cover that, but happy to do that as well. And otherwise, I will keep trekking on, and we will be building up to Fourier Series in maybe 2-ish episodes. Yeah, we'll see how it goes. Okay, so let me know if you have any other questions, and thank you very much for watching. We'll see you next time. Bye!